recently, in the past few months, on anomalous Hall crystals in rhombohedral multilayer graphene. So this, I would like to highlight my collaborators first. So this is a collaboration between the two coasts. On the Harvard side, we have we have Tomo, who is a new postdoc at Harvard, and my advisor, Ashwin Vishwanath. On the Berkeley side, we have two fantastic grad students, Taiga and Tianle, from Mike Zaltow's group. And and Mike Zaltow himself, and my long-term collaborator, Daniel Parker, who's now starting at University of California in San Diego as an assistant professor. So the main character of today is going to be electronic crystals. Yeah. And when we think about electronic crystals, we think Wigner crystals. Wigner in 1934 proposed that electrons, if you have strong enough interactions or low enough electronic densities, will automatically break translation symmetry and form into this array, closely packed array of localized orbitals. And this has been actually visualized very, very recently. This is an experiment, STM experiment from Ali Astani's group. In a magnetic field, they put electrons into lambda levels, and at certain electronic fillings, electrons form triangular lattices, and basically these red dots are where the electrons are sitting at. This is not a phenomenon that is related to magnetic field. The Wigner crystallization can also appear without magnetic fields. But this is also a very recent experiment from Feng Wang's group, and they use some complicated optical imaging techniques to visualize electrons, I think, in TMD systems. And what they see is that electrons form puddles of Wigner crystals, these quite regular arrays. However, there's one unsatisfying thing about Wigner crystals. That is, they are topologically trivial. Here I'm showing a charge density profile of Wigner crystal obtained from Monte Carlo. And you can see that Wigner crystal is basically just an array of localized orbitals. However, usually when you have a topological electronic system, you fill some topological band. And topological bands are not made of localized orbitals. When you linearize wave functions of topological bands, you necessarily need to get power law tails, and they're not exponentially localized. So I think there is an interesting question to be asked here, which is there even a possibility to get a topologically non-trivial Wigner crystal, a Wigner crystal that carries a non-zero Chern number? In fact, this was first studied by Tessanovich, Axel, and Halperin in 1989, in which they proposed this concept of Hall crystals. What they did is they engineered some quite complicated interaction for electrons in lambda levels. They put electrons in magnetic field, and they control the filling such that the electronic filling is exactly one per lambda. Is exactly one per magnetic flux. So electrons will exactly fill one lambda level. And due to the engineered interaction, they showed that under Hartree-Fock approximation, electrons will spontaneously break translation symmetry to form a state which is a crystal, but also has a Hall response. And here, the Hall response is really due to the magnetic field that you have applied to the system. What we want today is the anomalous version of the Hall crystal. The anomalous Hall crystal refers to the following thing. It appears at zero magnetic field, and it has continuous translation symmetry. However, it has a non-zero Hall response, meaning it has non-trivial Chern number, and it spontaneously breaks continuous translation symmetry. This state we will call the anomalous Hall crystal. Yes?
How unrelated to like quantum Hall sprites? bubbles and lots of all the quantum bulk calculations. So in terms of translational symmetry, stay very common there. So how is it different?
This is a great question. So my understanding of it is the following. Quantum Hall stripes usually appear in higher lambda levels. For example, at fillings, for example, 3.5 or 5.5, then these stripes will form. And if you just look at, for example, if we're talking about the let's say the fourth lambda level, you put half of the electrons into the fourth lambda level, and you look at those electrons as a whole, they will form a Chern number 0 charge density wave. So the charge density wave part is topologically trivial, and the rest of the electron in lower lambda levels will contribute a Hall response. That's what's different here. So in that case, for example, in the Hall crystal regime, you're really in very low lambda level index. You're really close to the 0th lambda level.
But from the observation point of view, from the symmetry point of view, they're different.
From the symmetry point of view, they are indeed not different. So if you simply stack a Wigner crystal on top of a if you simply stack a Wigner crystal on top of a Chern insulator, you will get something, if you package as a whole, something like an anomalous Hall crystal.
But you're not really stacking, you're still doing the whole structure form with the magnetic field, with the your lambda level is lambda level, right?
Yeah.
So what those people did was not stacking.
Well,
I don't know how
in the stripe business, right? In the stripe business, the lower lambda levels that contribute the Hall response and the electrons that form stripes are really, separate entities. Okay, thank you. All right, so today we're gonna take a journey towards the anomalous Hall crystal. I'm going to first discuss the very exciting experiment from Longju's group of rhombohedral pentalayer graphene, which motivated us to first think about the anomalous Hall crystal. And then in part 2, hopefully I will convince you that we have constructed a very minimal phenomenological model for the anomalous Hall crystal state. All right, so given that Longju has just come back a few days back, I will hopefully this part will be very straightforward. The experimental setup is the following complicated stack, but the main character is this material called rhombohedral pentalayer graphene. So by pentalayer, I mean that there are 5 layers. So each one of these layers is a layer of graphene. And they're stacked in this way such that neighboring layers form staircases. And this stacking is called rhombohedral. Apart from that, they also encapsulate this rhombohedral multilayer graphene stack with 2 slabs of HBN. HBN crystals have a very similar lattice constant compared to graphene. So when the 2 crystals are closely aligned, they form a moiré pattern. Indeed, there is a moiré pattern formed by the top HBN, but not the bottom HBN. This is very important. Apart from that, they also have 2 gates. The top gate, both gates are made using graphite. And by tuning the voltages of those 2 gates, you can control the electronic density within the rhombohedral pentalayer graphene and a perpendicular electric field across the rhombohedral pentalayer graphene independently. This perpendicular electric field we'll call the displacement field.
Your statement that there's no moiré on the bottom, that's because the twins
Yes.
are too large.
Yes, it's completely unaligned, right? The top one is aligned, the bottom one is unaligned. Yes, great. So here are the experimental observations at very high displacement fields. So this is something that people have not previously attempted. What they see at moiré filling 1 is a Chern insulator, something that has Rxx equals to 0 and Rxy equals to 1 in units of h over e squared. And what you see is that as you lower the electronic filling, if you dope holes on top of the nu equals 1 state, you get fractional states that are insulating with fractional Hall conductance. These fractional states are called fractional Chern insulators, and they're analogs of fractional quantum Hall states in the absence of a magnetic field. They have been long sought for. In fact, this is only the second only platform to appear to host these states. The first platform was twisted MOT2, which was studied by experimentalists at University of Washington, Qingfei and Jieshan here, and Tingxin Li's group back in Shanghai Jiaotong University. So perhaps this cut this line cut at a certain displacement field is much more illuminating. You can see that there are a bunch of plateaus, with fractions 2/5, 3/7, 4/9, 4/7, 3/5, and 2/3. I would like to particularly highlight, the fraction 4/9, which has quite a large denominator, just illuminating how the quality of the sample. Okay, as theorists, we're very interested in this material, of course, due to all the fractional states. But as it turns out, the integer state was already puzzling on its own, right? In fact, if you look at the setup, you immediately find a huge mystery. As I have alluded to before, right? The moiré potential really sits on the top layer, right? The effect of the HBN alignment is really on the electrons on the top several top layers. However, you apply a huge electric field, and the electrons are going to get pushed down to the bottom layer. So effectively, if you just look at those electrons, they should not feel a very strong moiré potential at all, which means that they really have graphene scale, or in this case, continuous translation symmetry. This is confirmed by just plotting the band structure. And what you can see is that there's no clear gap induced by the moiré potential. The effective moiré potential is very, very weak.
Right.
Yes.
By huge, let's say we put in numbers, what is the density difference between the top and the bottom layer?
Something like, something like 10%. On
90 versus
10. 1 versus 10, yeah,
Okay.
something like that. Yes.
You did a different experiment where both of them were not giving moiré pattern. Presumably, then you would predict that they would still see this event.
Okay, you're jumping 3 slides ahead. Great. We'll touch on that very soon, right? Okay, and this immediately defies the current way that we understand these fractional Chern insulator states. The usual way we think about it is the following: you take an isolated, very flat Chern band, you take it and you put some electrons into it, usually at a fractional filling, and those electrons will form, some fractional states that are similar to lambda levels, and you're happy. However, here there isn't even an isolated Chern band to begin with, let alone talking about any of the fractional Chern insulators. So the first step for us is to generate the Chern band. As it turns out, what happens is that the interaction will stabilize a Chern band. This is self-consistent Hartree-Fock numerics, so completely mean field. What you see is that a Chern band gets separated out. This state breaks time reversal symmetry because all the electrons get polarized into one of the valleys due to the large density of states. So all electrons occupy this Chern band. just as a technical detail, this is Coulomb interaction projected to a large number of bands, and we completely freeze the valence bands. So we assume that all the valence bands are completely filled, and we only do numerics on the conduction bands alone. What is particularly interesting is that this single particle charge gap is determined by the interaction. You can change, forms of your interaction, of your moiré potentials to be, there has been debate about, how the actual HPN creates the moiré potential. And in this calculation, the gap is nearly unchanged. And, if you can scan a bunch of parameters corresponding to different twist angles between the rhombohedral graphene and the top layer HPN and displacement field, what you see is that at low angles, you get a Chern number 0 insulator. At large angles, you get a metal. And in between them is this very broad phase of a Chern number 1 insulator, which I will argue to be an anomalous Hall crystal in the next slide.
Well, what's the spin state for the Chern? Like, is it spin polarized as well?
Yeah, it is spin polarized, yes. Also due to the same reason, large density of states, solar ferromagnetism. Yeah, great. So yes.
You have said just in the calculation, is moiré in it or not?
This calculation, moiré is in it. Okay. Now, as very acutely pointed out by Chaoming and Jim, the question is, do we even need a moiré in this case? And the answer is, of course, no. Now, this calculation is done without moiré. Here, of course, we're still using mean field approximation. We compare the energy of a translationally symmetric metal versus the Chern number 1 insulator, right? And what you find is that above a certain critical displacement field, the Chern number 1 insulator wins. And of course, as I have said before, like the charge gap is completely insensitive to the moiré potential. It's only a function of dielectric constant alone. This critical displacement field actually decreases as the number of layers, and so but the Chern number 1 insulator still survives in different number of layers. So, if there are any experimentalists listening to this talk, please make 6 layers and and 4 if you can crank up the potential. So, what I would like to argue, at least in the current approximation, which is a very strong one, in the mean field calculation, what we have found is that this state, a Chern number 1 insulator that spontaneously breaks translation and spontaneously breaks time reversal symmetry. And thus, this is exactly what we are trying to find. This is an anomalous Hall crystal. Yes. Sorry.
So for this calculation, are you still assuming the band folding in the moiré pattern, but just turning the moiré potential to 0?
Yes. So what we do is that we explicitly choose a Brillouin zone that fixes the way that the band is folded. So yeah.
So the spontaneously broken translation symmetry is fed into it.
You can also, do try to optimize over different ways of breaking translations. That is also possible. Yeah.
Relates to my confusion. So it sounds like you're doing stoner ferromagnetism, is it right?
Which part?
So is the mechanism large density of state stoner ferromagnetism in some channel? Is that?
The translation breaking is indeed induced in this way, yeah. So basically the band is very flat, right? And okay, so the way I usually think about it is the following. If you have perfect nesting, then, of course you wouldn't be surprised that, translation is broken. Then if, the band is flat enough, it does not cost a lot of kinetic energy to deform your your Fermi surface into one that has perfect nesting, and this gives you
How is the Fermi surface getting? Who is deforming?
you know the after the deformation of the Fermi surface, it can gain interaction energy by breaking translations.
So you want to break two things. You want to break tangle and
Yes. Yes.
So, and breaking time reversal in stoner ferromagnetism is just the density of state effect.
Yes.
And that, but that's not like orbital magnetism, or is it like, is there a pseudo spin somewhere? Maybe I missed something.
Okay. So
You're doing something like stoner ferromagnetism, which you could do either with real spin or with pseudo spin.
yes. So
What is the pseudo spin label?
the K and K prime. So there are two values.
You're valley breaking.
Yes.
So you're valley breaking, you're valley polarizing, and you're getting translational symmetry breaking because of that also?
We're getting translation symmetry breaking because the band, around the valleys. So for example, if you look at, the band structure around the point K, then the band is very flat. That will give you.
So what sets the periodicity?
What sets the periodicity? The electronic density sets a periodicity.
You're going to look at a Fermi surface and try to find something that best nests. Is there warping involved or?
Here, I don't know what's the precise meaning of the warping, but we do take into trigonal warping, which is yes.
Because you need to somehow
Oh.
get a length scale out of something.
Yeah.
And why do they happen simultaneously?
Why do they happen simultaneously? So
You can break the valley, you can induce CDW, they don't have to happen simultaneously.
indeed, they do not have to happen simultaneously, and as we have seen for many times, they do, in fact, most of the time do not happen simultaneously. Why this happens simultaneously? Probably, yeah, I don't have a great answer for you at this
But
moment. Yeah.
your picture of the state is valley polarized charge density.
A valley polarized, I would want to say Wigner crystal, because charge density wave almost implies that you originally have a lattice and you're just breaking discrete translation symmetry. Here, it's really incommensurate.
But I just want to understand from the symmetry standpoint, what is it?
In that sense, it's a valley polarized charge density wave.
You're driving it by nest.
Yeah, something like that. That breaks continuous translation symmetry and topological quality. Great, thank you.
One thing to clarify, so
Yeah.
it's actually related to this question. If this thing exists purely in continuum, the density does not have to conform to whatever the moiré scale gives you.
Absolutely not.
Principle, they can even fight against each other.
Yes.
But I suppose in the real system, somehow they magically turns out to be same ballpark, same number.
3 slides later.
Okay.
But yes, but no, indeed, they do turn out to be, the same magic number that, basically one way to think about this is, the moiré line scale gives you a Brillouin zone, and the Brillouin zone, within the Brillouin zone, you can look at how flat your band is. The folded band, the bottom band of your folded band structure. If that folded band structure is very dispersive, you're not going to get dispersion. And it just happens that the electronic density and the moiré potential just fits together such that the dispersion is very, very flat. Yeah.
Why don't you get a space superconductor?
Why do I not?
With the game that you're playing, it is easier to get a space superconductor.
How to say this? So one, I don't really. Okay, how to say this? So one, indeed, in lower number of rhomboheterographing, the superconductivity is seen, right? For
But I mean, that's experiment.
in my calculation, I mean, in this case, I'm using repulsive interaction. I'm not sure where the attraction between electrons could come in here. I'm not sure what's the glue for the Coupe pairs.
You can get supersymmetry out of purely repulsive interaction.
That's from soft modes or something, right? Or
You can do like that.
oh, I see.
Different way.
I
But
see.
so within your mean field theory, you're doing repulsive interaction, which will only give you maybe ferromagnetism and CPW.
Yes, we have not considered. Yeah. Thanks a lot. Okay, I guess everyone agrees that this is a cool state. I would like to also highlight some simultaneous works. A whole bunch of them from Sentel's group at MIT, Yahui's group, Jianpeng Liu's group, and Andre's group. Particularly, Yahui's group also found that the Chern insulator in this setup could be interpreted in the framework of spontaneous translation symmetry break. And of course, upon doping this band that was just formed, you can find fractional Chern insulators. The band is quite flat, and it has very decent quantum geometry. The trace condition violation is not very large. And when you put holes in them, this at nu equals 2/3, you will find fractional Chern insulators in both exact diagonalization through spectral flow and DMRG through entanglement spectrum. All right. There is a caveat that I would like to warn everyone against. These calculations are projected into the Hartree-Fock band structure that we have obtained. So we have restricted our effective Hilbert space to the orbitals that are forming the anomalous Hall crystal band. This is, of course, a quite uncontrolled approximation, and we know that it would become false when the electronic filling is much less than 1. For example, at nu equals 0.01, the Hilbert space is definitely not correct. And in fact, you probably need a more sophisticated method to find the correct Hilbert space. Yes.
So you first did Hartree-Fock.
Yes.
Get the flat bands,
Yes.
then you do some numerical. Are you double counting interactions somehow, or like how do you make sure that you're not double counting interactions?
Good. So what we do is the following. After you perform your Hartree-Fock, after you perform your Hartree-Fock procedure, you get your field states, and you start from the normal ordered interaction with respect to charge neutrality and project into this Hilbert space. That is a completely legal procedure, and in that sense, we're not double counting the interactions. And yes, as you pointed out, there is a real danger of doing so. All right. Now, for the $1 million question, is the experimental state a crystal? We want to be cautious here, right? There is indeed an optimistic possibility that the experimental state, if you completely don't have moiré potentials on the top layer and the bottom layer, the system is completely translationally symmetric. It might be a crystal. And what the actual experiment that Long has performed shows is that the moiré potential actually pins the translation breaking pattern and to a certain lattice. There is a less optimistic scenario, which is also likely, which is that maybe the ground state in the absence of a moiré potential is actually translation symmetric. It's not a crystal. However, this state has a very large susceptibility without a moiré potential. So you need a very small but still finite moiré potential to get an anomalous Hall crystal state stabilized. Yes.
But your susceptibility Q will be determined by your Fermi surface, and that does not have to be in any relationship with your moiré Q.
I guess that would definitely, well, right. So indeed, if you applied a moiré potential that is whose wave vectors are completely off from your KF and whatnot, then the crystal will not form, right? And so these are speculations.
Do you know?
Do I know the KF? actually, if you just look at the non-interacting band structure, the Fermi surface for the band structure I have plotted is quite complicated in the sense that it actually has a Mexican hat shape, and thus if you just very naively fill the lowest energy orbitals, you would get an annular Fermi surface. And in that sense, I don't know if we should use the inner one, you should use the outer one, you should use the average, something like this. But yeah. Anyway, so I would also like to highlight the danger of claiming victory with Hartree-Fock, which is the tendency to form crystals is way overestimated if you just do mean field theory, because Hartree-Fock cannot capture the energies of gaplet states very well. In fact, for the Wigner crystal, it overestimates the tendency to crystallize by a factor of 15 in interaction strengths or in RS. So we're by no means claiming that the state is definitely a crystal here. Okay. There's, of course, also a question of, what is actually the moiré potential in the experiment, right? Because of modeling difficulties and whatnot, this is actually quite complicated and needs potentially more work from both theoretical and experimental fronts. What I would like to highlight is that, as pointed out by the paper from Andre's group, there is a potential enhancement of moiré effects by the interactions due to different vacuum subtraction schemes, basically how you choose your charge neutrality, the state which represents your charge neutrality point. So difficult problems. Okay, so this concludes the first part of the talk. During the process of modeling this very exciting experiment of rhombohedral pentalayer graphene, we found an interaction-induced Chern band that is surprisingly robust against many perturbations, and this even survives without a moiré potential. And thus, at mean field level, we claim that this state is an anomalous Hall crystal. So far, I have presented you with just numerical observations, no physics discussed. In the second part of my talk, hopefully I will, I will talk about this minimal model that we have constructed to explain what we have observed numerically. Yes.
Within the current setting, can you explain why the change of sign of the electric field would destroy everything?
We do. And so in fact, there's a very simple understanding. If you just polarize electrons to the side where moiré is present, the moiré potential will localize the electrons.
The regular.
Well, I wouldn't call it a Wigner crystal. It's a trivial insulator, right? Yeah, and equal one, you have, yeah. Exactly. A fully filled topologically trivial band. Yes. Yeah. So, however, there are also debates along that front because you don't actually know what's the form of the HBM potential you have to choose. You don't know how strong it is. Blah blah blah. Yeah, difficult problems.
Those should have just not aligning.
You would think not aligning things are not very difficult. But I guess making samples are also very difficult. Rhombohedral stacking is not the most stable stacking. Yeah. All right. Moving on to the second part. So to understand why the anomalous Hall crystal state even appears in our numerics, we have to understand properties of the anomalous Hall crystal state a little bit better. First of all, we can look at its charge density. Its charge density has nothing like the Wigner crystal, which are triangular lattice shaped. This actually has a honeycomb shape in which you can see that there are two peaks in the Brillouin zone and one dip. Right. Wigner crystals are usually strongly coupled, but the anomalous Hall crystal state that we have found is actually very weakly coupled. Here, on orange lines, I'm plotting the dispersion of the system, which gives rise to the anomalous Hall crystal. And in this gray shading, I'm plotting the interaction strength. What you can see is that the interaction cannot completely rearrange the band structure, right? For example, the state at gamma here cannot be strongly mixed with states up there, simply due to the interaction not being strong enough. This weakly coupled nature is also shown in the following quantity called the band number. Basically, what I do is that I take a field orbital from the anomalous Hall crystal state, and I calculate how many non-interacting bands does it live on. At gamma point in the middle, the band number is 1, which means that it corresponds to simply living on one non-interacting orbital. Whereas if I look at the kappa and the kappa prime points, the band number is 3, which means that the anomalous Hall crystal orbital is basically a linear superposition of 3 non-interacting orbitals. What's probably most surprising about the anomalous Hall crystal is its patch-like structure. What I'm plotting here is the following. I take an arbitrary momentum q, take the field orbital, and I overlap it with high symmetry point orbitals, such as gamma, kappa, and kappa prime. And then I take the maximum of those overlaps. And you can see that in most of the regions, the overlap is rather large. What this tells you is that, for example, orbitals around gamma, but not exactly at gamma, behave almost like they are like the gamma electron. And electrons which are close to the kappa point behave very similarly to the kappa point electrons, and similarly for the kappa prime electrons. Yes.
So should I be surprised by this? Is this? I don't have a good intuition here. Is this?
Should you be surprised at this?
I guess so. I guess there's also the statement that the wave functions at the different symmetry points are orthogonal to each other.
Of course, in Rhombus pentalayer graphing, because you have many different atoms, they will correspond to different. They will give you a spinor structure in the orbitals, and the spinors at this point and this point indeed look quite different.
So is there, if I had a different model or looking something different, would I expect, instead of getting these big patches, do you get small regions, or is this?
This depends. I think the intuition is that this depends on how fast the spinors change, right? If here this spinor is very different from the kappa point spinor, then you surely wouldn't expect this to occur. And it's actually the Fock. I think our understanding is the Fock interaction really tries to align the spinors from the kappa point and nearby points. And because Fock interaction wants spinors to point in the same way, they create patches. So to enhance the Fock interaction, you want the spinors to look very similar to each other. Yes.
Surely you're ignorant, but there's very striking zero along straight lines between those colored patches.
Oh no, that's me enhancing the visualization of the patches. Yes, yes. No, thankfully those aren't. Yeah, it's not so discontinuous. So this feature actually motivated us to construct a minimal model called the 3-patch model. And the goal of the 3-patch model is to explain why is this Chern number 1 crystal even favored against, Chern number 0 crystals, such as the Wigner crystal. What we're going to do is to impose some assumptions, some of which might not be, a priori justified from controlled approximations, but in the end, you will see that this model works very well. Yes.
Is it argument to solve just why is value polarizing? Why is this such a complicated problem?
the valley polarization, that is right. But okay, how to say this?
Figure out like why was that?
No. So that is actually not the problem, right? So for example, if I go back to this slide, right, maybe a little bit even further back, right? If I go to this slide, all of these electrons are valley spin polarized. However, some of them still give rise to Chern number 0, in this case, crystals, right? So there's a question to be asked, which is, why aren't all of these regions, which presumably the electron crystallizes, go into a crystal we are familiar with, the Wigner crystal? Why aren't all of these the Wigner crystal? Why do you get something for which the Chern number is not 0? That's the question.
You broken time resistance.
Indeed, right. So broken time reversal symmetry gives you the possibility for non-zero Chern number, but it does not guarantee that it's going to be non-zero. Yeah, thank you. Right, going back. So what we want to understand is why does it choose the Chern number 1 state? Right. So we're going to impose some assumptions. We're going to assume valley polarization from the beginning due to Stoner ferromagnetism from a very large density of states from the fat band bottom. We're going to do mean field approximation and just to make progress. And we're going to assume that the states are going to be translation breaking. So this excludes the possibility, the competition with metals from our model, because if we do mean field calculations, we're not going to be responsibly taking into account correlations for the metals. Anyway, so and furthermore, we're going to assume that the state is weakly coupled due to relations that we have alluded to above, right? Interactions are only going to mix low energy orbitals. For example, this 3-fold degeneracy at kappa point, 1-fold single band at the gamma point, and etc. The most important approximation that we're going to make is this 3-patch approximation, which basically says that states which are close to the high symmetry points look almost exactly like the high symmetry point wave functions. What this enables you to do is that you can basically delete all the electrons in the Brillouin zone, which are not at the high symmetry points. They get absorbed. This is like a very coarse graining block spin approximation. All the electrons around the high symmetry points gets absorbed into the electron at the high symmetry points. So, right, how many electrons are there? There are only 3 electrons in states of this model: 1 at gamma, 1 at kappa, 1 at kappa prime, and that's it. To make the discussion more explicit, we're going to construct the 3-patch states. Given that we're filling electrons at the high symmetry points, particularly here at the C3 high symmetry points, the occupied orbitals must form representations of C3, which are labeled by the angular momentum L.
So is the 1 at gamma essentially we're getting?
No. So as you can see, the gamma point, in fact, is completely fixed among all these 3-patch states, and we will explicitly show that gamma point wouldn't matter at all. And we can use this property that the gamma point doesn't break translation symmetry to fix the C3 action such that the angular momentum at the gamma point is 0. The kappa and kappa prime points are slightly more complicated. For example, for the kappa point, it can form a linear superposition of orbitals here, here, and here, corresponding to different spinor structures. These electronic orbitals are guaranteed to be energetic, to be degenerate in the single particle spectrum due to C3 symmetry. So as you can see, this superposition, linear superposition takes this form, which means that these angular momentum are really well-defined mod 3. So for kappa point, there are 3 choices that you can take: angular momentum -1, 0, and 1, and 3 choices for the kappa prime point as well. Thus, there are 9 states in total. One choice from the gamma point, 3 from kappa, 3 from kappa prime. What? Yes.
This is a very dumb question. What's this kappa referring to? What is the Brillouin zone?
It's the edge. It's the vertex of the Brillouin zone. So Brillouin zone looks like this.
Right. Another Brillouin zone or the moiré Brillouin zone?
Moiré Brillouin zone.
You just said.
Very good. So what we do is that we explicitly choose a Brillouin zone such that in each unit cell there is 1 electron. This will fix the size of the Brillouin zone. Yes. Sorry. In this phenomenological model, the electronic density matters. So
Is there 1 electron per graph, the cap layer moiré pattern facing?
okay, so all of these calculations, you should think, there's no moiré whatsoever. Yes.
The question you're asking is, what about that whole moiré pattern you started?
Mm-hmm.
Are there lots of electrons per unit cell of that moiré pattern? Are there few electrons? Are they equal?
This is a great question. In fact, we don't assume that those things will be commensurate in this case.
Are they far apart? Can we know that this pattern is nothing to do with that one because it's so much different than that?
This is a great question. In fact, so what I want to say is that I don't know the answer because we had just completely thrown away all moiré effects in this model.
I mean, presumably experiments have some idea how many electrons they have.
In the experimental setup, those are very much on the same order.
They're similar.
Almost exactly the same. So the
Electrons are pushed to the bottom, but the number is set by the moiré.
Oh no, the number you can tune by hand, right? The number of electrons within the graphing stack you can tune by hand by controlling the voltages.
And then they see all this interesting phenomena when they're near the density 1 per moiré pattern.
Yes.
Even though the moiré pattern doesn't matter.
That's what we are saying. Yes, because.
But you agree that
I completely agree, which is what we have said before, right? So in those cases there is a competition between the length scale when they are far apart. There is a competition between the moiré. The moiré wants to impose 1 translation breaking pattern. The electrons by themselves probably want to impose another translation breaking pattern. And this competition we have not studied before.
And the experiment, if the density that's far away from the moiré length, it doesn't behave the same way, or they just won't there because that's the way they thought it.
If the electronic densities are very, very far more, so if the electronic densities are very, very large, the other effects are going to come in. For example, the dispersion is going to become super large.
Make it that quite different, but not crazy, so that it's this.
At 1/2, so if you lower. At that point, I think the claim is that they form a composite Fermi liquid whose charge density, whose translation breaking pattern is still set by the moiré.
Was all of this motivated by the Hall plateau at fractional filling?
Was all of this motivated by? No.
What was motivating all this?
The motivation of all this was to, even get to just understand the possibility of getting a Wigner crystal that is topologically non-trivial.
Oh, so this part has nothing to do with any experiment?
No. I might have.
So what was the experiment that motivated this? That must have a building.
Sorry. The experiment motivated the first part of the numerics. This part.
Yes.
The first part of the numerics motivated the second part of the model.
Whichever was, what was the building in the experiment? Wasn't it some commensurate fractional building of moiré?
Right. So let me try to understand the question, because I assume that I've incurred some confusion right here. So you're asking, when does the Chern insulator, the integer Chern insulator, occur in the moiré experiment? Is that the right question to answer?
Oh, it just sounds like there's a lot of debate about whether your periodic whatever is, I mean, your periodicity that you are assuming here, that you have one electron per some periodicity.
Yes.
What is the relationship between that and the moiré due to Bien? There is some confusion about that.
Right.
So I want to know, in the experiments that motivated all this adventure, what was experimentalists know the building, and there was something incompressible, plateau-like, or something sharp in the experiment
Yes.
that motivated a lot of theoretical investigation. I just want to know what the building was.
Oh no, that feeling is one. That feeling is exactly one. Yeah.
Okay.
Yes.
1 electron per.
Moiré. Yes.
Right.
Yes.
Okay. So why do we want to insist that this periodicity that is exactly same as moiré periodicity has nothing to do with moiré?
You know, how to say this? Moiré, as we have said, right? You know, realistic consideration is one thing, right? Realistically, this system might just need a moiré to form a Chern insulator, which we can debate on. On the other hand, the urge to understand why we can even see something like this without moiré in numerics is something that we are trying to address.
There's the thing. Okay, so your theory using this heartbeat clock and things like that gave you moiré even without gave you this
insulating state
crystal even without a moiré pattern.
Yes.
And now you're trying to understand why you're seeing your heartbeat clock gave you this answer.
Yes.
And this is the reason your heartbeat clock is giving you that answer.
Yes.
And if the experiment also made use of the moiré, good for it, but it doesn't matter.
Yes.
Okay.
But the problem is in Hartree Ball, the periodicity you're going to get has no reason to have any relationship with the moiré periodicity.
No, not at all. Not at all. Completely agree.
So experiment was just some inspiration. You shouldn't try to relate this to experiment.
Very yes, almost exactly. No, yeah. You know, if experiments does have something to do with this, then we are going to be ecstatic. Yeah. Yes.
Well, question about the culture defense, we're going to generally for like the pentalayer graphene.
Yes.
Holding the light.
Yes. Yes. Great. All right. So on with explaining why the translator appears in our numerics, right? What this simple modeling, simple modeling might seem very minimalistic, but it does not lose all the flavors it does not lose track of all the global data. In fact, there is a perspective called symmetry indicators. Basically, when you have some symmetries such as C3, you can only look at orbitals occupied at those high symmetry points, gamma, kappa, and kappa prime. And what Bernwick and folks have proven is that if you add those angular momentum together, you're gonna get Chern number mod 3. And for the model that we're considering, what's gonna happen is that all the states with the same Chern number can be related with different translations. And this will reduce the number of different 3-patch states from the previous slide of 9 to 3, corresponding to the 3 Chern numbers, C equals -1, 0, 1, mod 3. So, yeah. Now we're going to evaluate different energies of three patch states of different Chern numbers. There are two parts to this. There is a dispersion and interactions corresponding to different electronic pairs. But not all of these care about the Chern number. In fact, there's only one term that cares about the Chern number, which is the interaction between kappa and kappa prime. What's going to happen is the following. We're going to evaluate the interaction between the kappa electron and the kappa prime electron using the Hartree-Fock approximation. So the Hartree-Fock approximation breaks the energy into two terms, the Hartree term and the Fock terms. Each of these, the Chern number dependent part of the Hartree and Fock are controlled by two scattering processes only. So scattering process from kappa 3 to kappa 1 and kappa 6 to kappa 4. And there's a similar one for Fock. What's particularly important about these scattering processes is their amplitude. Basically, a combination of form factor. When you calculate the amplitude of this process, you have to overlap the spinner at kappa 3 to a spinner at kappa 1 and 6 to 4, and you multiply them together and whatnot.
So is it like the weak to strong pairing transition of QH?
I'm not sure I really understand the weak to strong transition between.
You're going to see a transition between having the winding number and not having the winding number, right? Like C equals 1 and 2.
That's right. That's right. But I'm not sure I have enough knowledge to make that comparison. Yeah. 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 That would be really cool. On the other hand, so what's going to happen is that if you just look at Hartree and Fock terms alone, then it's really the angle of these scattering amplitudes that determine what Chern numbers that they favor. So Hartree favors one Chern number due to one angle, theta h. Fock favors another Chern number due to this phase factor, theta f. But in reality, the energy of the Hartree, the three patch states is going to be a weighted sum of those two, plus a Chern number independent term. However, what's going to happen is that in the phase diagram, as a function of theta h and theta f, sometimes you can get frustration-free regions in which both the Hartree and the Fock favor the same Chern number, at which time you can guarantee that your state has a certain Chern number. So for example, for Hartree between 0 and 2 pi over 3, all of these regions favor Chern number 1 for Hartree. And when theta f is between pi over 3 and pi, all of these regions also favor Chern number for Fock. So when they overlap, you can guarantee that the ground state is Chern number 1. Hopefully at this point, we have convinced you that the spinners determine the form factors, the form factor determining the scattering amplitudes determine energetics. So the spinners are quite important. Given the time, let's try to do this very quickly. We need to find out the spinners for rhombohedral multilayer graphene. Rhombohedral multilayer graphene is basically a SSH chain with hoppings VFK in plane and T1 out of plane. And SSH chain has a topological phase when VFK is less than T1, and you have exponentially decaying boundary modes living on the two sublattices, one on the B sublattice living on the bottom, and one living on the A sublattice on the top. And they're going to be mixed together if there's no displacement field separating, which gaps them out. However, once you apply a displacement field, you're going to find that the spinner content of, for example, the conduction band is basically described by this spinner alone. Well, now we're going to produce these spinner. We're going to choose a Brillouin zone corresponding to 1 electron per unit cell. And what you're going to find is that the spinners at all the high symmetry point is controlled by this number called eta. eta basically describes how large the Brillouin zone is. So eta basically is how long this separation is, and physically it can be tied to the square root of the electronic densities. Now we're gonna apply the three-patch model to rhombohedral multilayer graphing, and you take a certain number of layers, by which I mean that you take the exponentially decaying spinner and you cut it off at certain components. Where you're going to see the phase diagram is very, very similar for 3 and 5. So this is 3 layers. You tune eta, which physically corresponds to you tune density, and there will be a phase transition between the C = 0 state at below eta at 0.6 or something, and above 0.6, it's basically Chern number 1. Let's skip this. Right. So given this transition, you can also compare it to the Hartree-Fock numerics that we have run. So this is this is the apex of the argument, right? We run self-consistent Hartree-Fock at different electronic densities and different displacement fields, different interaction strengths to see what is actually the parameter that drives this transition. And what you can see is that there's a pretty clean phase diagram as a function of eta. Above eta equals 0.5 or something like that. All the insulators that you get are Chern number 1, below which most of the insulators have Chern number 0. You can also tune, microscopic parameters, such as the hoppings. You can tune hoppings by 20%. And if you convert the phase boundaries to eta, you find that it only moves on something like 2%. So I think what the three-patch model has identified is this crucial tuning parameter called eta, and this has been revealed to be true in microscopic numerics as well. So by this, I think we claim victory over explaining our own numerics with this very simplified model with 3 electrons. I would also like to highlight some other models that also have models for anomalous Hall crystals. There's one paper from Jennifer Cano's group. There's one paper from Tritz's group. And again, our old friends Senthil came to almost exactly the same model as us. Given this development in anomalous Hall crystals, there are many questions to be addressed. Can we apply this three-patch model to more materials? Can we do something beyond mean field that is exactly solvable or most likely analytically solvable? And what about the phonons in this topological crystal? Is there a possibility for fractional anomalous Hall crystals? And what is the role of moiré potential and disorder? With that, I would like to conclude the modeling of this very exciting experiment in rhombohedral graphing has inspired us to think about the state of anomalous Hall crystals, and we have built a three-patch model, three-patch phenomenological model for the anomalous Hall crystal that we have found in our numerics, and it is decently successful. With that, thank you very much. Questions, answers? Wow, silence. Yes.
I'm just imagining what fractionally filled system.
Yes.
And you're thinking you're fractionally filling your spontaneously generated Fermi surface. Wouldn't it just make not Fermi surface?
Whatever. Yeah.
Crystal.
Yeah.
Wouldn't it just choose the new density to make it?
No. So this is.
Sometimes break that to get a fraction.
Right. No. This is a fantastic point in which this is, we want to study this, but this question in particular, but I have not found a very good way to phrase to to probe the problem. So probably one way to say this is the following, right? Let's say you have some particular electronic density, and at which you get the anomalous Hall crystal. Then you dope holes, you decrease your electronic density. At, for example, filling 1/3, let's say, right? Let's say 1/3. There are two possibilities. One, you keep the density, the translation breaking pattern unchanged, and you form a fractional state, most likely, and the fact that you can just expand your unit cell and form an integer filled state. There is non-trivial competition between those states.
But if the only thing that's setting the lattice constant is the density of electrons.
Yeah.
Change the density of electrons. How can it be ever fractionally filled?
Exactly. That's what Wigner crystal is supposed to be. Wigner crystal's periodicity should be only set by the density. If you really want to insist on name, but that's semantic. Okay? As far as I can tell, what you have is a valley polarized charge density wave state, which the valley polarized state on by valley polarizing side can or may not have Chern number, right?
Yes.
But you, in your second paper, you indeed treated translational symmetry breaking totally separately from your Chern number physics.
Yes. Yes.
So as far as your translational symmetry breaking is concerned, you're getting it out of higher sensibility of nesting, which is what Chern is doing.
Basically, yeah. No. Going back to the question, it's although I agree with the sentiment, I do not know if there is a precise argument for which one can argue that it's always going to be the integer state rather than the fractional state. In fact, we have been looking for this argument for a very long time without success. So yeah.
If there is no way to set the lattice constant, and if the lattice constant of the electron lattice is purely except by interaction,
Yes.
you have to define the periodicity as the lattice.
No,
There's no way to talk about fraction.
I agree. So basically, my question is, right, at a particular electronic density, there are two possible states, one fractional, the other integer, right?
You cannot talk about fraction if you don't have lattice.
Right. So electrons will spontaneously break translation symmetry to form a lattice, and the lattice, if you calculate the electronic density, electron number within each unit cell of that lattice formed by electrons is fractional. That's what I mean by fraction. I mean,
You've shown by your original calculation and new calculation that there is a tendency, there's this enhanced susceptibility, as you said before, for a Chern-like state with the periodicity to form that maybe the experiment is making use of by having a very weak moiré perturbation.
That would be,
and that blocks it that.
Yeah.
And then the experiment might want to look at fractionally filled such state. And your mechanism would frustrate that the fact that you need an enhanced susceptibility to the moiré state is allowing the system to do this interesting thing. And if you try to put a third as many electrons or half as many electrons, then it's losing the advantage that your mechanism is providing, and is now having to
I agree with the sentiment that, you know, maybe wouldn't it be so nice? Like, okay, how to say this, right? RBB is not, it's probably not the ground state for cuprates, and yet people have studied RBBs. This is by no means RBB, but theoretically, I think it is still worth pursuing. Yes.
Assume there's no moiré potential and you're intrinsically a continuum limit where you have a continuous translation symmetry. And the thing is is very different from the mechanism, because that is very different from the Wigner crystal at lowest model level, in the sense that when you try to increase your charge density, you always your sigma xy is always get pinned to one.
Yes.
While in the Wigner crystal at lowest model level, although it's only the crystal, but the sigma xy goes with the charge density.
Wigner crystal.
So
Whoa.
go the lowest half and very the low amount of electrons, then you can
When, for example, 1/7, indeed, I do get a Wigner crystal state, but I'm not sure you get sigma xy proportional to the density. Oh, I see. Okay, let me say this. Probably what you're thinking of is the translationally invariant case. The translation invariant, the straight up formula is slightly difficult there, right? In the completely clean case, right, the Wigner crystal is not an insulator because you can expand, first of all, it can slide. So the sigma xx is non-zero. Two, it can, you can dope into it by shrinking the lattice constant. So it's by no means an insulator. So straight as formula, but it doesn't need to hold in that limit. If you read Burst's paper in 1989 is actually called Hall crystal versus Wigner crystal, and I think in the reference somewhere in the reference he has a discussion on the straight up formula, basically, if the charge density is the charge density pinned by the magnetic field or something else, he says the straight up or the sigma xy. He says the straight up formula can only be used if the Wigner crystal is pinned, meaning it becomes a true insulator. So it can slide, right? The Wigner crystal can slide like this. If there is no disorder or potential making it pinning it.
yeah, but that
No, I mean, what you're saying is correct. What you're saying is correct. In the clean limit, I agree that sigma xy is proportional to the density. However, in experiments, I'm not sure the experiments at nu equals a seventh, it has sigma xy non-zero. That's what that's not clean. The clean limit. Yes. Sorry. Yes, I should have made that clear. Yes.
okay, but in your framework, that's in the clean limit, your have consistency, you have continuous consistency, and you increase the charge density, but you are still an insulator, and there's not quite
You need pinning. You need the pinning to make sure that this is an insulator. Otherwise, I don't even know how to think about this. But once you add a little bit pinning, which means that you're necessarily away from the clean limit, then sigma xy, is pinned to 1, which I agree.
Your state is yeah, your state is hard density way. It is an insulator.
No. I have continuous translation symmetry, right? I have a continuous translation symmetry, which means that my state can slide and expand. So it's exactly the same as the Wigner crystal without pinning. The Wigner crystal without pinning is not an insulator.
But I thought you were getting nesting. driven charge density wave in your new field theory.
Yeah.
That gives me a charge density. Charge density wave is charge density. It will have equity non-linear effects.
That I can probably agree with, but translation, like given continuous translation symmetry, right?
Well, I think I'm really lost because you're Fermi surface and to talk about building needs lattice to start with. So I don't know why are you insisting on continuous translation symmetry? I know what Hartree Fault does. I know what charge density wave is. And the statement that you want to make by associating to bigger crystal seems to be a philosophy, not something that comes out of calculus.
I'm not sure I agree.
Because the calculation at the level of your calculation, your Hartree fault is the same as all quantum Hall Hartree fault. The difference is that you're breaking valley symmetry, and in that valley spinor physics, you may or may not have turnover. But as far as translational symmetry breaking out of Hartree fault mean field theory, it's exactly the same thing as quantum Hall stripes and quantum Hall bubbles. And they didn't say what they have is some bigger crystal breaking translational symmetry. Although they start actually with translational symmetry. It's a
No, okay. So I agree. I agree that I can agree with the fact that you can choose to call it a charge density wave. However, what I'm not sure is that the physical response will be significantly different.
So you think it is charge density wave, but you think the physical response will be different from a charge density wave?
For example, what response are you considering?
That's
I think that
different from bigger crystal.
CW in the clean limit. So CW, even though it drifts, even though it drifts, do you still think that it is an insulator?
Okay, so you want to consider it being pinned.
Yeah,
It's not different.
when it's being pinned, then we're all clear. I think that's the limit in which we can agree. When the crystal cannot move, then everything is clear. It's a good insulator. Sigma RxY is whatever value that the Chern number is.
I'm sorry, but I just need to understand this because I listened to Ajmin's talk and also I was really confused then too. So it looks like, do I understand this correctly? Calculation is same as that of charge density.
What is the
Physical observation will be the same as charge density, but you want to think about it from a different perspective.
I'm not sure I understand either of the two claims that has been made. One, the calculation is exactly the same as charge density wave.
As far as the translational symmetry breaking is concerned, that is used access through Hartree fault mean field theory, the faults of Fermi surface in some lambda level, like say.
Well, lambda level doesn't have a Fermi surface. So
the Hartree fault calculations of stripes start from lambda level and they can get different lambda levels and they do Hartree fault and they get a translational symmetry break.
Completely agreed. Yes.
That's exactly what you're doing.
That's okay. That's one way to interpret what we're doing. Indeed, we both use Hartree fault. We both find translation symmetry. Both find translation symmetry breaking. Yes.
But you didn't start with lambda.
I indeed did not start from lambda levels.
But you don't, that's, he was also starting with something that's flattish. That was important, right? Starting with a flat band.
Oh, yeah, sure.
My band was the surface versus okay, whatever.
Density of state, you can consider repulsive interaction, you can't get charges.
Sounds good.
Have density.
Agreed. Okay, sorry. Is the confusion resolved or not resolved?
Resolve.
Okay.
I don't understand why you guys want to associate from a different, you want to look at it from a different perspective, but that's your choice.
I usually let me
I just want to know what it is.
let me
But now I understand.
let me say one last thing about this. In quantum Hall, the charge density waves, the stripes and the bubbles usually occur at commensurate fillings of the magnetic unit cell. So within each unit cell, there's, a rational number of, or an integer, I'm not sure which one it is at this moment, can't calculate on the fly. But that is commensurate. Here, nothing is commensurate, right? So in that case, I can agree with, in that case, I would still argue that something is setting a lattice, which is the magnetic field. At least, the size of the unit cell is set, has an integer relation with the unit cell size set by the magnetic field. There's no such scale in this in the setup that we have considered.
It's virtue, not a vice. A moment ago, you were saying, maybe I can get fractions. Now you're saying that the lattice is set by the density.
Indeed, okay, probably that is another thing to be considered here. We are okay, let me make this very clear. We have never in our calculations claimed to say that we have obtained a crystal with fractional, a crystal with, fractionalization. We have never said that. All the fractional calculations were done in a setting with Moiré potential. And, even if we obtained something in the fractional setting without, even if we got a fractional state that spontaneously breaks translation symmetry, I don't think we have, the capacity to claim those states right now. Right now, the only responsible claim that we can make is that in the integer state in our numerics is translation symmetry breaking. The fractional states are not, and we do not have capacity to claim them.
So one of the things I thought you said earlier
Yes.
was that I don't know about these other calculations, but your electron states, your electron band
Yes.
that form the Chern stuff
Yes.
are the same as the electron band that you use break the symmetry. And in the charge density wave, whatever it was, you were saying that the Hall part was very different from the electron states that are forming the charge density.
Sorry, so this was referring to Una's question in the beginning part of the talk, where this is referring to quantum Hall stripes, right? So indeed that is the case. That is indeed an interesting distinction. Indeed, that is the precise distinction that I want to make here. There, at least in our system, you cannot make it is a, how to say this? The aspect that the electrons have topology and the aspect that the electrons break translation symmetry are not separable.
But your second calculation was separated. You started by breaking translational symmetry. You said
the calculation
by having no translational symmetry already broken.
The calculation might
separated into calculations.
The calculation might have been separate, but you cannot find two groups of electrons that, for which one breaks the translation and the other contributes to the topology. I do not think you can make that distinction. Indeed, you have to do two separate steps of the calculation, which I can agree with, but I do not think that.
Since we've been having a discussion for a long time, so interested people could continue discussion and the others can do briefly do.
Wait.
You need to value, you have to break the value symmetry without having a value consider and not get to the front.
Sigma access. I do not know.
Within the confound and the